Good day to Dr. Jumardi. My name is Sharmaine Tan, and today our group are pleased to present our topic on high pressure processing and advanced non-thermal technology used to enhance food safety and quality, especially in microbial inactivation. Before I proceed, here is the mind map that represents our overall structure for the topic. It gives a quick visual summary of important aspects of high pressure processing.
I'll be talking about principle of HPP. First is the Lee-Chatelier's principle, where the reaction or the process that involve in a decrease in volume are favored by pressure. HPP accelerate chemical reaction, phase changes, or structural shift that reduce volume because applying pressure pushes the system towards a smaller volume state. Next is isostatic principle, where the pressure is transmitted uniformly throughout the product, regardless of its shape or size. When the food is compressed, pressure acts equally in all directions so that the product maintains its shape after processing. This allows the different food forms and package to be treated effectively. The third principle is the principle of microscopic ordering, where it increases the pressure leads to greater molecular ordering at a constant temperature. Pressurizing material causes molecules to become more structured or ordered, which affect the physical properties of food.
Figure above illustrates the main components of a typical HPP system. As shown in the diagram, the pressure vessel is the central cylindrical chamber where packaged food products are loaded. This vessel is engineered to withstand extremely high pressures, up to 600 megapascal. Surrounding the vessel is the pressure transmitting medium, usually water, which fills the chamber. When pressure is applied, the medium ensures the force is distributed uniformly throughout the product, regardless of shape or size. To achieve this, the system uses a high pressure pump, which forces water into the vessel until it reaches the target pressure level. This pressure increase can be seen in the diagram, where the pump is connected to the vessel through hydraulic lines. The closure system is located on both ends of the vessel and safely seals the chamber, preventing leakage and ensuring operator safety during processing. Finally, the temperature control system monitors the natural temperature rise during pressurization, known as the adiabatic heating, helping maintain stability and enhance microbial inactivation.
Now I will explain the key parameters involved in HPP. These parameters are important because they determine how effective the process is for ensuring food safety and maintaining product quality. The first parameter is pressure level. HPP uses very high hydrostatic pressure applied to food, typically between 100 to 600 megapascal, which is the commercial operating range. Higher pressure means better microbial inactivation. Next is temperature. Although HPP is considered a non-thermal process, some heat is generated during the compression. The processing temperature usually ranges from ambient to about 60 to 65 degrees Celsius, depending on the product. Holding time refers to how long the product is kept at the target pressure. This can be from just a few seconds up to more than 20 minutes, but commonly 1 to 15 minutes is used in industry. Next is compression rate. It is the speed at which pressure is applied. This can vary widely, usually between 1 to 300 megapascal per minute depending on the equipment. Other than that is decompression rate is the speed at which the pressure is released. It can range from very fast, just a few seconds, to a few minutes. Fast decompression can sometimes cause physical changes in delicate foods. Next is pressure transmitting medium. HPP requires a medium to transmit pressure uniformly. Common pressure transmitting media includes water, glycol solution, or oils, but water is the most widely used because it is safe and efficient. Other than that is packaging material. For HPP, the product must be packed in flexible packaging material like ethylene vinyl alcohol are preferred because they can withstand high pressure without breaking. Next is type of microorganism. Different microorganisms respond differently to pressure. Generally, gram-positive bacteria are more resistant, and bacterial spores require even higher pressure for inactivation. Other than that is food matrix composition. The composition of the food also affects microbial survival. Proteins, fats, and carbohydrates can protect microorganisms, making them harder to inactivate, so the effect varies depending on the food. Next is pH. pH is another important factor. Food with lower pH are even sensitive to pressure, meaning microbial inactivation becomes more efficient. And lastly is the water activity. Water activity affects microbial protection. Foods with low water activity can protect microorganisms, making pressure treatment less effective. In summary, all these parameters, pressure, temperature, time, packaging, and food characteristics work together to determine the success of HPP in ensuring food safety and quality.
High pressure processing contributes to three different effects, such as effect on microbes, enzymes, and nutrients. For effect on microbes, the pressurization causes the interruption in nutrients transportation and respiration process of the microbes due to alteration in cell membrane permeability, which leads to lack of the nutrients in cell, and finally the cell death can be occur. For effect on enzymes, it will also cause the denaturation of functional protein, which reduces the movement of proton and thus reducing the intracellular pH value. At 60 megapascal, it will cause damage in protein structure, while in 300 megapascal, it will cause irreversible denaturation. Hence, it is efficient in microbial inactivation. For effect on enzymes, HPP is a non-thermal method and able to preserve the nutrients. It has only minimally effect in macronutrients, including the protein and carbohydrates, but no effect for micronutrients, such as vitamin and minerals of the particular food materials.
HPP shows different levels of effectiveness depending on the food matrix. In food-based products, HPP is highly effective. For example, apple juice treated at 150 to 400 megapascal can achieve up to an log reduction of E. coli. Mango juice also shows strong activation of E. coli or 157H7, and mango pulp records high reduction in yeast, molds, coliforms, and lactic acid bacteria. In comparison, seafood products show lower pressure effectiveness. Fish slurry treated at 250 to 400 megapascal resulted in smaller reductions, especially for Listeria monocytogenes. This is because the protein fat matrix protects the microorganisms. The black tiger shrimp also shows only moderate reduction under similar pressure conditions for organisms like E. coli, Staphylococcus aureus, psychotrophic bacteria, and aerobic mesophilic bacteria. These examples highlight how food composition significantly influences HPP performance, with fruits allowing higher microbiome inactivation, while seafood products tend to protect microbes. That's all from group HPP.